All right then, your attention please. Sheet 2, work power energy, given to you a long time ago. Let's solve some MCQs from the sheet, right? A particle of mass m moving in a circle of radius r with constant speed v. The force on the body is mv squared by r. We know that centripetal force, mv squared by r. What's the work done by this force in moving the body over half the circumference? Obviously 0, because at every instant force will be perpendicular to the velocity. The power associated with this force is going to be 0. It's never going to do any work. This work never changes the kinetic energy of this force, will never change the kinetic energy of the particle. It will only change the direction of motion of the particle. Therefore, it will never do any work, right? Let's look at problem 2. So 0, work done by this force, centripetal force, is 0. So here we have an elevator, a thread, mass m, tension T. The elevator has an acceleration a upwards. We want to find the work done by the tension on the block during t seconds, right? So if I have to write the equation of motion of this in the ground frame, then T minus mg must be ma in the ground frame of reference, right? So the tension in the thread is m into g plus a, right? Then in the ground frame of reference, this point P in t seconds must have moved to P prime, the point of application of t, by an amount half at squared must be the displacement in the direction of t. So the work done by tension on the block must be T into S, which is m into g plus a by 2 into at squared. That must be the work done by. Yes, displacement is 0. In the non-inertial frame, work done by t is 0. That means in the elevator frame of reference, the displacement of this point is 0. So work done by t is going to be 0 in the non-inertial, the elevator frame of reference. Absolutely. All right, problem 3. Three systems given to us. One, okay. In each of these cases, you know, the free end of the rope is pulled with a force F. Okay. By an amount 2 meters. The point of application of the force moves down by an amount 2 meters. We want to find the situation in which the kinetic energy of the block is maximum by the time this is pulled down by 2 meters. Right? All right. See, in this case, when this is pulled down by 2 meters, when this point P comes to this point P prime by 2 meters, what we'll do is we'll apply work energy theorem to a system that comprises the string plus the mass. so that I don't have to, the moment I include befriend the string, I don't have to deal with the tension in the string. That means I include the string in the family, right? So it will not pull me anymore. Okay, so a force F applied, right? Then the only two external forces, if I include the string in the family, then the only two external forces would be F and mg, if the string is included in the system, right? Right? So for this, when this goes down by 2 meters, this must move up by 2 meters, string consideration, right? Okay. So work done by F is F into T. Work done by mg is minus mg into 2, minus mg into 2, and this must be change in kinetic energy of the mass, starting from rest, half mv squared here, right? 2 meters up. That's for situation 1, right? For situation 2, look, when this goes down, this pulley moves up, right? See, as far as this pulley is concerned, this pulley, the moving pulley, do you realize that when the moving pulley moves up by x units, then it will release x units here, x units here. That means this length will decrease by x, this length will also decrease by x. That means to the right of this pulley, the string length will decrease by 2x. Yes or no? And that 2x must come down. That means in this case, 2x is 2 meters, so x must be 1 meter. So in this case, x is 1 meter. That means while this goes down by 2 meters, the mass m must move up by 1 meter. Are you all okay with this? Right? Right. So then once again I apply work energy theorem to a system that comprises the string, the pulleys, and the masses. Right? A mass, one mass. So F into 2, situation 2, F into 2, right? Minus mg into 1, work done by gravity, and this must be change in kinetic energy. Right? Work done by gravity is mg into 1, negative sign, right? Come down to this. This again moves down by 2 meters, right? Hey, do you realize that if this pulley moves up by x meters, right, this length will decrease by x, this length will decrease by x, and the mass is also moving up by x meters, isn't it? If this pulley moves up by x meters, this mass will also move up by x meters. So this length will decrease by x, this length will decrease by x, this length will decrease by x. That means this plus this plus this will decrease by 3x. Where did it go? It must have appeared here. That means 3x must be 2 meters. So this must, 3x is 2 meters, x must be 2 by 3 of a meter. That means this would have moved up by 2/3 of a meter, yes or no? See, if this goes up by x meters, this pulley will also go up by x meters, right? So this length will shorten by x meters, this will shorten by x meters, this will also shorten by x meters. That means this plus this plus this will shorten by 3x meters, which will appear as 2 meters of descent here. So 3x must be 2 meters, right? So x must be 2/3. So this mass m moves up by 2/3 of a meter. Clear? Right? So apply work energy theorem to a system comprising the string plus the masses, the pulleys. Then I get F into 2, work done by this, minus mg into 2/3, and that must be change in kinetic energy. That's for 3. So this is the smallest, so this will be the largest. So change in kinetic energy will be the greatest in 3 and smallest in 1, as you can see. Clear? Okay, let's move. Why will it be same, Khoka? No, this is change in kinetic energy for this situation. This is change in kinetic energy for this situation. This is change in kinetic energy for this situation. That's what it means. Is that all right? There are two springs, one with force constant K1 and pulled with a force F, the other one with force constant K2 and also pulled with a force F. K1 greater than K2, that's given. When they are stretched by the same force, we want to find which force does greater work, right? Hey, if this is elongated, it will elongate to an extent x, it will elongate by an amount say x1, such that the external force F will be balanced by the spring force x1. Only to that extent it will elongate, right? This force F will create an elongation x1 such that kx1 will take care of F. It won't elongate any further. So the elongation here is going to be F divided by K1. F divided by K1 is going to be the elongation of the first one. The elongation of the second one is F by K2 is the elongation of the second one. The work done by this is going to be F into x1 because this point of application has moved to the right by an amount x. So F into x1 would be the work done here, F into x2 would be the work done there. So the work done in this situation is F into x1, which is F squared by K1. Similarly, work done in 2 is going to be F squared by K2. And it's given that K1 greater than K2. So W2 will be greater than W1. Problem 5. So this is a circle of radius r being drawn by a pencil with a normal pressing force n. N is the normal pressing force. N is the force with which I am pressing it and I am drawing this. So then, if I am going this way, there would be kinetic friction acting this way. If I am going this way, kinetic friction would be mu k into n acting this way. Right? Yes. Whereas the displacement would be ds to the right from instant to instant. In order to go from this point to its neighboring point, you need a displacement ds tangential, right? So work done by Fk is going to be minus Fk into ds. The total work done by friction would be sum of all of this. Fk does not change with time, comes out. Sum of all the ds's will give me the total length of the circumference, which is going to be 2 pi r. That's the work done by friction. Is that okay? A body of mass m starting from rest accelerates to a speed v0 in t seconds. The work done on the body till any time t. Hey, till any instant, this is till time t0. In t0 seconds, it accelerates to a velocity v0. So what is its acceleration? v0 by t0 is the acceleration, right? In t seconds, what would its velocity be? At. At would be its velocity, which would be v0 by t0 into t would be its velocity. So then the total work done would be change of kinetic energy. Work done is going to be change of kinetic energy, which would be half m v squared, means v0 by t0 into t whole squared. That's the change in kinetic energy. right? That's going to be the work done, change in kinetic energy. 7. Is that all right? I expected you to have solved all these independently too, right? So it's only a formality that we are solving it on the board, but you should have got it right yourself as well. Problem 7. A force F given by K yi cap plus xj cap is taken from a point P 3, 5 to a point Q which is 5, 7, and we want to be able to find the work done. We want to be able to find the work done. Now, apparently they have not told us the trajectory. That means this work done must be independent of the trajectory. That means this force must be a conservative force, right? Otherwise, without knowledge of the trajectory, we cannot calculate the work done if it's not a conservative force, right? But let's check that out, right? Oh, okay. All right. In any case, let's take it along any trajectory. How does it matter, right? We will not even require the need for a trajectory. So from a point M, which is x comma y, if I have to take it to a nearby point N, which is x plus dx, y plus dy. That means from M to N, the displacement is dr. From a point M, x comma y, the displacement would be dr tangential to the curve, right? And the dr is going to be given by dx I cap plus dy j cap, right? The work done by this force is going to be F dot dr, is going to be the work done by this force. Yes or no? And F dot dr, if I took the dot product, then it's going to be k y dx plus x dy is going to be the work done to go from M to N along a, right? So then this, if you realize, is going to be d of xy, right? So then the total work done would be sum of all the dw's, which would be k times integral d of xy, where xy initially is 15 and xy changes to 35. Yes or no? So xy, which is the subject of integration, changes from 3 into 5, 15 to 5 into 7, 35. Hey, integral dt will always be t, isn't it? So this is integral dt. So that's going to be t, which is xy, right? So this is going to be k times xy, where xy changes from 15 to 35. So that makes it 20 k joules of work, path independent. That means this kind of a force will be a conservative force. This kind of a force is going to be a conservative force. Work done is not dependent on the path, straight line or curved, right? Number 8. Your attention, please. Don't lose heart. Prabhu. Yeah, why not? No, but why not? If you like to come here and do the it's no issues. All right. A light spring of length 20 centimeters this is the spring of length 20 centimeters. Unstretched length of the spring is 20 centimeters. With a force constant K, which is given by 2 kilograms per centimeters. Hey, generally force constant is measured in, let's say, dynes per centimeter or newtons per meter, etc. In this case, if they say 2 kg per centimeter, that means when I write F equal to kx, that F should also be in kgs. You know what I'm saying? If I use K as 2 kilograms per centimeter, I can convert it into newtons per centimeter. How? I can multiply this by 10, it will become 20 newton per centimeter. But I don't have to, because then if I have to use F equal to kx somewhere, force in the spring as kx, then that F should also be in kilograms, kg weight. That's all, right? So then there will be consistency in dimensions, right? Are you all there with me on this? Right. So this is placed vertically on a table. A small block of mass 1 kg falls on it. A small block of mass 1 kg falls on it. All right. And obviously when it falls, let's say it has a velocity v. When it falls, it has a velocity v, which would be, let's say, root 2gh, the height from which it falls. That's not important. We want to find the length h from the surface of the table at which the ball will have a maximum velocity. See, let's get it straight. When it strikes a spring here, it has a velocity v. It therefore begins to compress the spring. It begins to compress the spring, right? This point P moves down. Now when it moves down, the spring exerts on this mass a retarding force upwards. The spring will exert a retarding force upwards, right? So the velocity of this will decrease. The velocity of this will decrease. In fact, not initially. Initially, it will not decrease. Initially, what will happen is, let's say, at the original point P, at time t equal to 0, it will not decrease. See, there are two forces acting on it. At this instant, there is only mg. When it just about strikes the spring, it has only mg, so its acceleration will be g downwards. Because the spring force is 0 initially. The spring is not compressed, so initially spring force is 0. There is only going to be gravity acting downwards, so its acceleration is going to be g, right? Now, from this point, which represents the point of natural length of the spring, after a while, it gets compressed. P comes to P prime, and the spring gets compressed by an amount x. Say the spring gets compressed by an amount x, right? No? So, the spring force will be kx upwards on the particle, and there is going to be Mother Earth exerting mg downwards, right? Now, as long as mg is larger than kx, it will have a downward acceleration and the velocity will go on increasing. Yes, Sasure, increasing. As long as mg is greater than kx, see, initially it's only mg, then kx, which is the upward force, which is attempting to retard it, will decrease the acceleration. Initially it's only g, then the acceleration decreases. Why? Because mg gets diluted via kx upwards, right? So acceleration decreases. mg remains the same all the time, but kx grows. So at some point of time, kx will become equal to mg, isn't it? So at some point, at a certain elongation, at a certain compression x naught of the spring, x naught from top, at a certain compression of the spring, we will find that kx naught becomes equal to mg. And at this instant, what happens is that the acceleration becomes 0. At this instant, the acceleration is 0, right? Yes or no? But by the time the mass has descended this, it has been accelerated all along. Therefore, by this time, it would have developed a velocity. It would have developed a velocity. The mass would have developed a velocity. This is the state where mg becomes equal to kx naught. Prior to this state, mg has been larger than kx. Before this state, the compression has been less than x naught and mg has been larger than kx. mg was the predominant force. Kx was smaller in magnitude. So it continued to accelerate. Although the acceleration decreased, the velocity increased. This is what happened. from this point P to this P. What is this P all about? This is the P where the particle has reached equilibrium. The particle has not come to rest, it has reached equilibrium. Equilibrium means no net force. Mg has been balanced by the spring force kx naught. Yes or no? Right? You know what I'm saying? Now, so from the topmost point to this position, what position is this? The equilibrium position. From the topmost point to the equilibrium position, velocity has increased. From the topmost point to the equilibrium position, the velocity has increased. But it's not that the particle will come to rest. Because of inertia, it would have developed velocity, it will go down further. It will compress the spring even more. But now, mg will remain the same, whereas kx will become larger than mg. If it depresses further, kx will become larger than mg, the particle will begin to retard. Yes or no? That means lower than the equilibrium position, the particle retards. Lower than the equilibrium position, the particle retards. So, just to take a fresh stock of things, from the natural length to the equilibrium position, the velocity has increased, though at a decreasing rate. There has been an acceleration, but the acceleration has decreased. So velocity has increased, but at a decreasing rate. So from the topmost point to the equilibrium position, velocity has increased. And from this point onwards, the velocity will decrease because there would be retardation. So would you want to believe that this point P must be the point of maximum velocity? The equilibrium position must be the point of maximum velocity. Yes or no? Right? Now, of course, if I use this K in kilograms, then I shouldn't add G. Then weight must be in mass, let's say kilograms. You realize what I'm saying? Then force should not be written as mg, force should also be written as m. Right? Because this will become kilograms per centimeter into centimeter kilograms. So this should also be kilograms. If K is in kilograms per centimeter, I should not write mg, I should write m as the force. Right? Whatever be it, the position of equilibrium, the position where the velocity must be the maximum. That's a point where the spring force is taken care of by the weight. Right? Which means the equilibrium position, x naught units from top, right? Spring force is kx naught, k is how much? 2. So 2x naught, right, is the spring force, is balanced by, this is in kilograms, right, because kilograms per centimeter into centimeters. So right, kilograms, and mass is how much? 1. So 1 kilograms. So 2x naught kilograms is balanced by 1 kilogram. Yes or no? So then that gives me 2x naught equal to 1. अरे महाप्रभु, ये किलोग्राम्स है तो फोर्स भी किलोग्राम्स में लेंगे ना. सो किलोग्राम्स ऑफ स्प्रिंग फोर्स बैलेंस बाय 1 किलोग्राम ऑफ बॉडी वेट, नहीं क्या? सो x naught then turns out to be half a centimeter, right? That means half a centimeter from top. V will be V max. That means 19.5 centimeters from the bottom. I'll tell you why there is no option. Because whoever must have said the option would have taken mg equal to kx naught. Now, if what you were thinking, I took this as 10. X naught will be 5 centimeters from top, matlab 15 centimeters from bottom. So if you make a mistake, you will get the right answer. The wrong answer, right? You know what I'm saying? So just whoever must have written these options must have made this mistake. You know what I'm saying? That's why he got one of these options. 15 centimeters is what the gentleman must have got. That's out of making a mistake, right? But it should be 19.5 centimeters from the bottom. That's the right answer. Not there in any of the options, right? Yes or no? Very good. Compared to a 4,000 kg spring? Yes or no? Work done by an external force would be change of potential energy. Work done by the spring force would be negative of the change of potential. So number 10, when a conservative force does positive work, work done by a conservative force will always be by definition, work done by the forces of the field would be negative of the change of potential energy, would be minus delta U. That's how delta U is defined. Work done by the forces of the field is negative of the change of potential energy. So if this is positive, delta U must be negative. That means if delta U is negative, change in potential energy is negative, that means potential energy must have decreased. Potential energy must have decreased. 11 is straightforward. I would expect you to be able to do it yourself. Let's look at 12. Right. So there is this 10 kg block. This is a circular arc of radius 10 meters. And this angle is 60 degrees. It's being pulled to the right. At the point P, the free end is being pulled by a force F equal to 200 newtons. If the block at A starts from rest, then by the time it reaches B, we want to be able to find the velocity of the block by the time it reaches B. Okay. Now, realize that on the block, the forces are mg downwards, right? The surface will exert normal reaction N, right? Now, what I'll do is, again, I'll make the string my friend. So, when I want to apply work energy theorem from A to B, I will include the block and the string as one unit. Block, string and the pulley as one unit. When I do that, then the tension becomes an internal force. I will not have to draw any compliance with that force. There would be then only 3 external forces acting on the system comprising the block and the string. What are the 3 forces? N, mg and F. That's all. Yes or no? Okay. Now realize that while it moves along this circular trajectory, the displacements are always along the tangent. So work done by N will always be 0. Yes or no? Right? So then from A to B, I choose to apply the classical work energy theorem. Right? Realize that mg has been acting downwards. This whole length is 10 meters. Right? Yes or no? This is 10 cos 60 degrees, 5 meters. This is 5 meters. Yes or no? A bit. 10 cos 60 degrees, 5 meters. So this will also be 5 meters. Right? So when the particle goes from A to B, its vertical displacement is 5 meters. mg is acting downwards. So what's the work done by gravity? Minus mg into 5. Minus mg into 5 is the work done by gravity when I go from A to B. Right? Now, this F. Realize when this goes from A to B, this is 10 meters, this is 10 meters. So this and this is 60 degrees. So do you realize that this must also be 10 meters? Because this is an isosceles triangle, and if this is 60 degrees, this will be 60 degrees, this will also be 60 degrees. So now an equilateral triangle, so this would be 10 meters. Right? So when the particle goes from A to B, this string shortens by 10 meters. So the point P must have advanced by 10 meters. So the work done by F must be 200 into 10. So work done by F is 200 into 10. And that must be equal to change in kinetic energy. Half mvb squared is the kinetic energy, and kinetic energy is 0 here. Yes or no? Where is it not? Here. No, it's going from A to B. Eventually the block is being taken from A to B. Right? So this will enable calculation of the velocity of the block when it reaches B. Clear? A particle is released from rest at the origin. So at x equal to 0, see, potential energy at any given x is given by x squared minus 3x. At x equal to 0, u is 0, and its release from rest, kinetic energy is also 0. When the particle reaches x equal to 2, I can find potential energy at x equal to 2. 8 minus 6, 2 joules, right? I'm sorry, 4 minus 4, 0, 6, minus 2. Minus 2 joules is the potential energy at x equal to 2. And if the kinetic energy is Ke at this point, then conservation of energy would mean this potential energy plus kinetic energy here equal to potential energy plus kinetic energy there. And this would enable calculation of kinetic energy at x equal to 2. Right? Let's look at 5. So there is m equal to 1 kg. The block and the wedge are initially held at rest. Now the wedge is given a horizontal acceleration of 10 meters per second squared. By applying a force on the wedge, so that the block does not slip on the wedge. That means there is no relative motion between small m and capital M. We want to find the work done by normal force in the ground frame. In the ground frame, I want to find the work done by the normal force between the two blocks. Between the two blocks, I want to be able to find the work done by the normal force, right? Now, look at this. The only two forces acting on small m are mg and the normal force, right? mg is doing no work. Why? Because small m is moving only to the right. Because there is no relative motion between small m and capital M, so small m moves only horizontally. So mg and the displacement of small m are perpendicular to each other, so mg is doing no work. The only work that is being done is by n, and that too the horizontal component of n, only the horizontal component of n. If that is n sine theta is doing work. N cos theta is passive, right? Okay. In any case, whether it's the horizontal component of n or anything else, the work is done by n. That's said to be the total work done by n, right? Now, in root 3 seconds, in a time t equal to root 3, what's the velocity of small m? A root 3? 80, v equal to 80, 10 root 3 meters per second would be the velocity of small m in root 3 seconds. Clear? Yes or no? Right? Therefore, there has been change in kinetic energy of small m. There is change in kinetic energy of small m, and change in kinetic energy of small m, which is half of small m into v squared. That must have been the work done on small m. And who's doing work on small m? Normal reaction. So this must be the work done by the normal reaction, half of m into v squared. Half of 100 into 3, so 300 by 2, 150 joules of work is done by normal reaction on small m. Yes or no? Clear? Let's look at 16. So there is a block that collides with the spring. Block of mass m, let's say it collides with the spring with a velocity v0 when the spring is in its natural state. There is coefficient of friction which is given to be 0.25 between the block and the ground. We want to find the speed of the block at the instant of collision. If this block is able to compress the spring by an amount 4 meters. If it's able to compress the spring by an amount 4 meters. Right? So, from this state of the block, state A to B, I'll apply work energy theorem. What are the forces acting on the block? The spring force, kinetic friction, which is mu mg leftwards, and then n and mg downwards. They are not important in this case, right? So I'll apply work energy theorem on the block between state A and state B. Okay. So first things first, what's the work done by mu mg? Minus mu mg into 4, yes or no? That's the work done by friction. Minus mu mg into 4. Mu mg leftwards, 4 meters rightwards. Right? Work done by the spring force is negative of the change in potential energy of the spring. The potential energy of the spring here is 0 because it's not stretched. The potential energy here of the spring is half k into 4 squared. Right? So minus u2 minus u1. Minus u2 minus u1 is the work done by the spring force. Negative of the change in elastic potential energy. So minus half k into 4 squared is the work done by the spring force. Right? And this must be equal to change in kinetic energy. Now if this is the state of maximum compression of the spring, then the velocity of the block must have become 0 here, because if it didn't, it would compress it further. Right? So this must be change in kinetic energy, which is final kinetic energy 0 minus initial kinetic energy half m v0 squared. So this will enable calculation of v0. Sounds all right? Let's look at 17. So we have a spring block system placed on a rough floor. Spring block system placed on a rough floor. This is the natural state of the spring. Spring of force constant K. Block of mass M. The block is pulled towards right to give the spring an elongation. X. Elongation X. Where this elongation x is greater than mu mg by k but less than 2 mu mg by k. Right? and it's released from this point. The block is released from this point. The elongation given is x larger than mu mg by k and less than 2 mu mg by k. Now, do you realize that kx here, the spring force, is greater than mu mg? Kx greater than mu mg? So if the spring is elongated by an amount x, the spring force would be kx to the left as shown, and which is larger than maximum static friction. Mu mg is the maximum static friction, so kx will overcome friction and the block will move to the left. Right? Okay. Which of the following principles of physics can be applied? Conservation of mechanical energy, conservation of momentum, work energy principle. Work energy principle can be applied to the block. Energy is dissipated because of friction. Friction will eat up energy, right? Momentum is not conserved because frictional force will deplete momentum, right? But work energy principles can be applied. Work done by this force and that force and some other force will always be change of kinetic energy. No, when we talk of mechanical energy, kinetic plus potential is not conserved here, because the spring force is eating up some energy, the frictional force is eating some energy, so mechanical energy is not conserved. Now see, in this position the spring is not stretched. There is no force acting on the block because the spring is not stretched. We would look upon this as the equilibrium position or the mean position. Now what we want to figure out is whether the block will be able to come from this point A where it's released to its original state B or not. That's what we want to check, right? Okay. If you say it will not, then you don't have to check anything. But if you say it will, then you will have to authenticate that, right? Either come to a conclusion that's acceptable or arrive at a conclusion which is bizarre that will reject your original assumption, right? So assume that it will reach B. When released from A, let's assume that it's going to reach B. For sure it will move leftwards because the spring force is greater than maximum static friction, so it will start to move to the left, right? If it starts to move to the left, what would be the frictional force acting on it? Mu mg to the right, kinetic friction. Let us say it's able to reach B. Let us say it's able to reach B, and by the time it reaches B, say it develops a velocity V0. Or if it just reaches B, V0 will be 0. If it just reaches B, velocity will be, V0 will be 0. Alright. So between this state and this state, I want to be able to apply work energy theorem, right? What's the potential energy of the spring at A? Half kx squared, right? Because the spring is elongated by an amount. What's the potential energy of the spring at B? 0, because the spring is unstretched, right? Okay. Work done by the spring force would be negative of the change of elastic potential energy, right? So that's going to be minus of 0 minus half kx squared. That means half kx squared. Negative of final minus initial is the work done by the spring force, right? So minus of ub minus ua, which would be half kx squared. That's the work done by the spring force. Work done by friction, minus mu mg into x. Friction is to the right, displacement is to the left. And this must be equal to change of kinetic energy, half m v0 squared minus 0, right? Now let's see if this is possible. Let's see if this is possible. What I do is, this I could take kx by minus 2 mu mg by 2. I could write it like this, right? Do you realize that kx is less than 2 mu mg? Kx is less than 2 mu mg, that's given. So this is negative because kx is less than 2 mu mg, so kx minus 2 mu mg is negative. Yes or no? Now this, if I say, is half m v naught squared, change in kinetic energy, then does it sound good? This is a negative number, kx minus 2 mu mg. So the left hand side is negative, right hand side is positive. So this is not possible. That means the original assumption that it's actually able to reach B is incorrect. It cannot reach B. Even if V naught is 0, even if this turns out to be 0, the left hand side is still negative. So it cannot reach B. As simple as that. It never does. Right? There is a toy car here. Initially at x equal to 0, and this point of ramp is x equal to 11, right? And when it goes from x equal to 0 to x equal to 11, it's under the influence of a force F that varies as is given in the diagram. F versus x goes this way, where this point is 11 at x equal to 11, and this point is 100 newtons, right? That's how the force decreases linearly from x equal to 0 to x equal to 11, right? The magnitude of the force. Now in one-dimensional situations, the area under the force displacement graph will give me the work done. Work done will be given by the area under the force displacement. So in its journey from x equal to 0 to x equal to 11, the work done by the force is given by the area of this triangle, right? So work done by the force is 550 joules, the area of this triangle. Yes or no? Right? So then, by the time the particle reaches here, work done by F is change in kinetic energy. It starts from rest here, and the change in kinetic energy here must have been the work done, which is 550 joules. But change in kinetic energy is actually the kinetic energy here. Is actually there because the initial kinetic energy is 0. So this is A, this is B. So I can say that the kinetic energy at B must be 550 joules, right? Now if it goes to a maximum height y max, then all this kinetic energy gets converted into potential energy. So then the maximum height y max is mg y max. M is given to be 5 kgs. So you can put 50 into y max is this 11 meters. Y max is 11 meters. Right? A wedge of mass capital M fitted with a spring of force constant stiffness K kept on a smooth horizontal surface, a rod of mass M kept on the wedge as shown, system in equilibrium. Assume that all surfaces are smooth, the potential energy stored in the spring. That means all that you need to find out is the compression in the spring, because if the spring gets compressed, then it will take care of the component of the normal reaction from this in the horizontal direction, right? So then if this fellow exerts on the block like before, so I'm not going to reinvent the wheel. The block, the wedge, will experience from this a n sine theta this way and a n cos theta this way. That's as far as the block is concerned. Yes or no? Yes, sir. We've done this before, so I'm not redoing this. N is the normal reaction between the two. So this rod exerts on the block a normal reaction in this way, which has a horizontal component n sine theta and a vertical component n cos theta. That's the story of the wedge, right? Now if the spring gets compressed by an amount x, the spring force kx acts to the right and will take care of n sine theta in equilibrium. So n sine theta for the wedge is taken care of by the spring force kx to maintain equilibrium in the horizontal direction. Right? Now, for the rod, if you look at the rod, there is mg like this, right? And as a consequence of n sine theta, reaction on it is n sine theta like this, oppositely directed, and n cos theta like this, oppositely directed, right? All the reactions will be oppositely directed, right? So vertical equilibrium of this would imply n cos theta must be mg, right? And what about n sine theta on the rod? Who takes care of n sine theta on the rod? हाँ right, ऊपर सही बोला. These supports will prevent n sine theta, this n sine theta acting on the rod, to have any lateral movement. If these supports were not there, you know, this sleeve is supported by these two. This rod is supported by a mechanical structure here, which will, yes, strut maybe, which will exert a n sine theta this way to prevent lateral movement of the rod. So n cos theta takes care of the weight, and then as simple as dividing, tan theta is kx by mg, or x then becomes mg tan theta by k, which would mean the potential energy stored in the spring is going to be half k x squared, right? Let's look at 21. Simple, na? Nothing difficult about it, except that you are tired and angry. I'm not tired, but I'm in pain. I can last forever. Let's move to 21, right? A block of mass m is hung vertically from an elastic thread of force constant mg by a. So this is an elastic thread, and say this is the natural length of the thread, L naught, and it has a force constant k given by mg by a, is the force constant of this thread. And there was a mass m hung here. The kinetic energy of the block when it passes through the equilibrium position. Now, need to understand what the equilibrium position is. Look, at this point, there is no force in the thread. Why? Because there is no deformation in the thread. The thread is in its natural state. The thread, during elongation, behaves like a spring. A rubber band, you know, this thread is like a rubber band. The rubber band in a compressed state or a collapsed state will not behave like a spring, but in an elongated state it will resemble a spring, right? So this is the natural state. I'm not collapsing the thread, so it will behave like a spring because the thread will only elongate from this point onwards. So its behavior is the same as that of a spring. Okay. Now, initially, is the mass in equilibrium? No, because the force in the thread is 0, there is no elongation, there is an unbalanced force mg acting downwards. So this is certainly not the position of equilibrium of the mass. You know what I'm saying? Yes, sir. No? Why is this not the equilibrium position? Because there is only mg acting downwards, unbalanced force, right? Okay. Now as the thread elongates, say when it is elongated by an amount x naught, right? The spring force would be kx naught upwards, whereas mg would be downwards. As it elongates more and more, spring force becomes larger and larger, mg remains the same. Initially, for a while, mg is larger than the spring force. Then at some instant, mg becomes equal to the spring force. When mg becomes equal to the spring force, that's the equilibrium position. Right? So the equilibrium position is 1 given by kx not equal to mg. That means when the mass has descended by an amount mg by k, there is the equilibrium position attained. Yes or no? Yes, but all along, from this point A, initial point A, to the equilibrium position, mg has been larger than the spring force. So the mass has got accelerated. By the time it reaches B, oh, okay, the force becomes 0, but the velocity is still non-zero. It has gathered velocity because it has got accelerated under the influence of mg minus the spring force. It has got accelerated. The spring force from A to B has been smaller compared to mg. The acceleration prevailed. Right? So then I want to find V naught in this state. So from A to B, I'm going to deploy work energy theorem. Right? What's the x naught? I have known the state of equilibrium. Right? What's the work done by gravity from A to B? mg into x naught. Mg downwards, x naught downwards. So mg into x naught. Right? Mg into x naught. That's the work done by gravity. What's the work done by the spring force? Negative of the change in elastic potential energy. Work done by the spring force is always negative of the change in elastic potential energy. The elastic potential energy here is half k x naught squared. The elastic potential energy here is 0. So minus half k x naught squared is the work done by the spring force. And that must be change of kinetic energy. It started from rest, so change in kinetic energy is half m v naught squared. You can plug in x naught equal to mg by k and solve for v naught. Does this sound fair? Comprehensible? Right? Very good. Okay, by the way, what happens after this? After this, it'll go down. But while it descends further, the spring force will be larger than mg. So it will retard. So velocity will become 0 somewhere. Now it happens, let's say, at some x, the velocity becomes 0. So from this state A to state C, I can once again apply work energy theorem to solve for x. Right? Between A to C, what's the work done by gravity? mgx. What's the work done by the spring force? Minus half kx squared. And that must be change of kinetic energy, which is 0 from rest to rest. That's the very best. Right? So that gives me x equal to 2 mg by k. Shabash. X naught is mg by k. Half of this. So this b is exactly halfway between A and C, because x naught is half of x, as you can see. Right now? Okay. Let's move to the next problem. क्या ससुरे, क्या बोल रहे हो? All right. Let's look at the next passage, 22 to 27, right? अरे कुशल इतने दिन अपने बाल बच्चों को छोड़ के कहाँ चला गया? वो तो और बाल बच्चों को यहीं छोड़ गया, किसके हवाले? जाएगा जा जा जल्दी जा क्या, नहीं आराम से जा क्या, हाँ ठीक है. So while he takes care of his natural requirements, let's read the problem and feel happy about the small little pause that we've got. प्रखर तू फिर जाएगा बिखर. I like your sense of humor. Huh? So, ready. You know, until a couple of years back, every time a new batch started, it would start on a very ugly note, because the first thing, or the first set of recommendations I had for people in the class were non-academic in character. That was about how to use the loo, what not to do, couple of things where I said, well, you still to learn projectile motion, but take care of some fundamentals. Two, the range is important. The range was important. Second, I very strongly recommended people to not leave traces of their intellect behind. Also, when it got very noisy, whistle or sing so that you can obliterate that noise and prevent people outside the washroom to hear the melodious sounds. And then there was a warning that I administered in the event. People fail to comply. I'm going to create a logbook here, time in, time out, so that I know who exactly was the culprit behind a certain event. If that also failed, then I would, yes. And if some people have not grown beyond the childhood, then I would send escorts with them inside. So, you know, every time I gave this instructions, though in a lighter vein, I found a bunch of parents taking very serious offense to this very mild note. So I thought, okay, let me not give them instructions. Let me just have some people tracking them. Now don't worry, we don't have cameras there. So we are only doing manual tracking. Let's look at problem 22 to 27. Huh? Precisely. Wow. Okay. So let's look at this passage, starting problem 22. Mass M, spring with force constant K. This mass compresses the spring and eventually comes to rest. The spring retards the mass and the spring eventually comes to rest. There are two observers, A standing on the horizontal surface, B. Whose was that? By mistake. What happened by mistake? Play it again. Don't change your ringtone, but change your phone. Okay? So there are two observers, one on the horizontal surface, A. Say there is an observer A here, and there is an observer B here. Assume this observer is massless. Okay? Now, to an observer A, see, while the spring gets compressed by a maximum amount, the mass moves by a maximum amount, the change in kinetic energy brought about must be at the behest of the work done by the spring force, right? Work done by the spring force must be change of kinetic energy, must be change in kinetic energy. So 0 minus half mv0 squared must have been the work done by the spring force. Work done by any force, work done by all forces put together would be change of kinetic energy. So final kinetic energy is 0 minus initial kinetic energy half mv0 squared. So work done by the spring force is negative minus, and you can see that because see, while the spring gets compressed, the spring force acts to the left, whereas this point P moves to the right. So naturally the work done by the spring force ought to have been negative. To an observer A, the work done by the normal reaction between the block and the spring on the block. Okay, see, at this point, right, that is at the point P, we want to be able to find the work done by the normal reaction N between the block and the spring on the block. What is it going to be? That's the same as spring force. This normal N is the same as spring force. So work done will be the same as what the spring force did. This normal force between the block and the spring at P is the same as the spring force. So work done by the spring force or work done by this normal force, that's the same. It means the same. Right? So minus half mv0 squared. To an observer A, the net work done on the block, minus half mv0 squared, because it's only the spring force that's doing work. So the total work done is minus half mv0 squared, right? According to observer A, ground observer, the kinetic energy of the block is converted into potential energy of the spring. Yes. Where did the kinetic energy go away? It got converted into elastic potential energy of the spring. Yes, A is true. B, the mechanical energy of the spring mass system is conserved. Yes. The kinetic energy of this plus potential energy of the spring here must be kinetic energy of the block here plus potential energy of the spring there. Yes, mechanical energy is conserved. Kinetic plus potential is the same. So B is right. The block loses its kinetic energy because of the negative work done by the spring force, right? The moment a certain force does negative work, it eats into the kinetic energy. If a certain force does positive work, it adds to the kinetic energy. If a certain force does negative work, it eats up the kinetic energy. Yes or no? Right? So the block loses its kinetic energy because of the negative work done by the conservative spring force. It's a true statement? No? Okay. A, B, C and D. To an observer B, now to an observer B, the block is compressing the spring. The velocity of the block is decreasing. Hey, no. What's happening to the velocity of the block for this? It's not changing. Is it changing, increasing, decreasing? What's happening? Huh? It's zero. It's zero. The velocity of the block is zero at all times for an observer B. It's on B, so it will report the velocity of this mass m always as 0. Right? Retardation of the block is increasing. What nonsense. Retardation of the block, is it increasing? Kinetic energy of the block is 0? Yes. Okay. Now, 27. According to observer B, the potential energy of the spring increases. Yes, it does, because this observer also finds that the spring is getting compressed, so the potential energy of the spring increases. This observer also finds this length shortening, isn't it? So the spring getting compressed, so potential energy increasing. Yes, very true. Due to the now where does it come from? The question is we need to address how this is happening, because this observer doesn't think that the potential energy of this is increasing because of the change of kinetic energy of this. An observer A, please listen to me very carefully. An observer A will certainly conclude that the potential energy of the spring is increasing because it's losing kinetic energy. But this guy says or thinks or perceives that kinetic energy of this is not changing, right? But the spring is still getting compressed, so he will have to address this issue. Where is the potential energy of the spring coming from? If it's not at the behest, please, if it's not at the behest of kinetic energy, where is the potential energy coming from, right? Now, due to positive work done by pseudoforce, never explain, I told you, never explain a physical phenomena with the help of pseudoforces. Now realize, very simple, to this observer has to explain how the potential energy of the spring is building up if it's not because of release of kinetic energy. An observer A will explain this. He says potential energy of the spring is building up because this is releasing its kinetic energy, which is appearing as potential energy of the spring. Yes or no? Yes. But this guy cannot say that, because to this observer there is no release of kinetic energy of the block, yet there is build-up of potential energy in the spring. Now this is what he has to say. Observer B, this is what he has to say. He says, well, there is a normal reaction N between the spring and this wall. The wall exerts a normal reaction N, right? Look at this observer A. The observer A finds that this point B is not getting displaced. So observer A will tell you that the work done by N is 0. The force that the wall exerts on the spring does no work. Let me not call it B, let me call this C, because B is the observer there, right? So observer A says that N does no work. Why? Because with reference to A, the point C is not getting displaced. Am I right? Okay, bless you. Observer B. Observer B finds that C is coming closer to this. Yes or no? As far as B is concerned, he doesn't think that he is going towards B. He thinks that C is coming to him. Yes or no? That's what this observer thinks. And therefore, the point C moves to the left. In a frame of reference attached to B, the point C is moving in this direction. Therefore, N is doing positive work. It's the work done by N. It's the work done by N perceived by B, which is adding to the potential energy of the spring. The potential energy in the spring is coming out of work done by the normal reaction the wall exerts on the spring at C. Do you understand this fact? Right? So work done by N in a frame of reference attached to B is half kx squared, the maximum elastic potential energy in the spring. Right?